Hello everyone, and welcome to today's webinar on trace and ultratrace elemental analysis of advanced materials by direct solid sampling and solution-based techniques. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted, however, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Dr. Rajiv Soman, Director of Purity Survey, will be answering some of the questions during the presentation, and we also have Dr. Larry Wang, Vice President of Electronic Materials Analysis, who will be available to answer SIMS-related questions. We will also collect these questions and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our presenter, Dr. Karis Falco, Scientist and Technical Leader at EAG Laboratories.
Thank you very much, Rena. Welcome, everyone, today to our webinar about trace element and ultratrace elemental analysis. Let's give a quick overview of what we'll be talking about today. After a brief bio of just myself, my name is Karis Falco. I'm a scientist based at EAG's Purity Survey Lab in Syracuse, New York. I joined EAG in 2017 after making the transition from academic to commercial sectors and have over 10 years of experience in trace and ultratrace elemental and isotopic analysis of inorganic materials. So we will start today's webinar with a brief introduction to EAG material science, followed by an overview of why and how impurity testing is important for many advanced materials. I will then provide you with some guides to consider when deciding to analyze a sample for impurities, and the range of services EAG offers to you from our analytical toolbox for this purpose, with a focus on the type of sampling they utilize, the materials they are most suited for, and their unique capabilities. So let's start with a brief overview of EAG. Eurofins EAG Laboratories is a global scientific company. We have over 16 laboratories in over 20 locations globally, and we serve more than 4,000 clients worldwide. Our 600 plus highly educated and highly skilled employees, combined with industry-leading state-of-the-art technology and equipment, enable us to leverage the power of science and engineering to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. Within our network of 16 labs, we have 18 that have instrumentation and staff with expertise in trace and ultratrace analysis located in the US, Europe, and in Asia. So to illustrate the specific techniques we'll be working with today, I would like to use the EAG SMART chart. SMART is an acronym for Spectroscopy, Microscopy, Analytical Resolution Tool. This concise visual reference tool is useful for comparing analytical techniques, detection limits, and analytical resolutions for numerous material characterization techniques. These encompass all of the trace and ultratrace techniques we'll be discussing today. Each bubble in the SMART chart, or bar, represents a different analytical technique. They are color-coded according to the descriptions in the lower left. For example, dark blue provide elemental information primarily, while green provides imaging information. Basically, spatial mapping techniques are shown inside the box, and bulk techniques are shown to the right. Imaging techniques are represented below the box. The x-axis shows the range of spot sizes for the analytical techniques from 1 centimeter at the right down to 1 angstrom at the far left. The y-axis shows concentrations either in atoms per cubic centimeter at the left or atomic concentrations at the right. So in this webinar, we'll be focusing specifically on trace and ultratrace detection ranges. In the context of this talk, the techniques we will be discussing today, shown here in the areas of the SMART chart not shaded out, or trace levels are defined as concentrations between 1 ppm and 100 ppm, or 10 to the 19 or 10 to the 17 atoms per cubic centimeter, and ultratrace as concentrations less than that. Now, achieving precise and accurate measurements of such small levels of elements is analytically challenging, often requiring complex instrumentation and a high degree of expertise. In recognition of this, EAG has become the industry leader in trace analysis analytical services. And to illustrate the breadth of our capabilities and to help you better understand how we can help you with purity surveys of your materials, we'll be focusing on some of our analytical tools that specialize in trace and ultratrace analysis. These are our SIMS techniques, our laser ablation techniques, solid sampling, GDMS, located here, solution sampling, ICP-MS, located here, ETV ICP-OES, and instrumental gas analysis, located here. So these techniques cover a wide range of different capabilities, such as depth profiling, 3D mapping, bulk solid sampling, and liquid analysis for trace, and in some cases, ultratrace concentrations. And while they are by no means the only techniques capable of analyzing low concentrations within our toolbox, they are technologically designed to be particularly excellent for this purpose. So why are we interested in impurities in many advanced materials? So the type, concentration, and spatial distribution of trace elements are of particular concern to many industries, such as electronics, aerospace, nuclear, and in commercial consumer products, such as impurities can affect the performance, the reliability, and the lifetime of many materials, parts, and devices, particularly under dynamic load and extreme environment or harsh conditions. But these are not the only reasons why purity testing is important. Regulatory compliance, such as restrictions on hazardous substances, supply chain testing, certification, a better understanding of new and evolving and emerging materials during research and development, are also very important reasons for the characterizations of trace elements in many materials. So this schematic illustrates some of the most impurity critical materials shown in orange in the middle, as well as their key physical or chemical properties in light blue in the middle, and dark blue on the outside shows their specific applications. The success of these technologies and industries relies on high purity feedstock and contamination-free processing and engineering. Trace elements can also be purposefully added as dopants in some materials, but often with strict controls on the maximum and minimum levels permissible. So let's take a look at some examples of materials that require good understanding of the levels of impurities within them. Our first is high purity alumina, which is largely used in consumer electronics, batteries, such as sapphire for smartphone glass, and as cathode and anode separators in lithium-ion batteries. The most important source of impurities in alumina is in the raw material used to produce it, namely bauxite, an ore extracted from topsoil, which requires an intensive multi-stage purification process using additional materials such as soda and lime that must be removed in turn during this process. Because of their impact on the performance and lifetime of the products they are used to manufacture, impurities in alumina are required to be limited to less than 100 ppm in total, as they can significantly affect behavior, such as the optical clarity of glass, or the crystallization of sapphire during growth, for example. So let's take another look at another example. This is high purity graphite, which is frequently used to manufacture semiconductor material and nuclear grade material. In particular, graphite used for nuclear applications is produced synthetically from pitch and petroleum coke and is heat treated to remove most impurities. However, controls on impurities in graphite used for these materials is very strictly controlled, as several elements have isotopes that can act as nuclear modifiers and reflectors in nuclear reactors, shown here in orange. The most important of these is boron, due to its strong neutron absorbing properties. As such, boron concentrations are required to be less than 2 ppm, along with several other elements shown in orange, which when combined are defined as the equivalent boron content. Great care must be taken to avoid any potential sources of contamination of any of these elements during graphite manufacturing. Additionally, graphite is an analytically challenging material that requires specific instrumentation to measure its impurities. In recognition of that, EAG has invested a lot of time and expertise and is now considered an industry leader in graphite analytical services. And finally, another example where impurities are important are in additive manufacturing, particularly for the 3D printed parts used in the biomedical, aerospace, and nuclear industries. The primary sources of impurities for 3D printed material are in the raw feedstock used, which can be composed of high purity metal powder or wire, ceramics, composites, glass, and also around 10% of feedstock is recycled back into production, but only after rigorous composition testing has been carried out. Of particular importance on these types of materials and parts is the impacts that impurities have on the structural behavior of the printed parts, such as embrittlement caused by hydrogen or oxygen impurities, and the distribution of impurities, which when concentrated can cause structural fractures, holes, and cause discontinuous melting, cooling patterns, and poor adhesion or inhomogeneous thickness in cladding layers, all of which can lead to catastrophic failures of parts. Okay, so let's move on to our next part. Bearing in mind the specific requirements that you are looking for, what kind of criteria inform a decision when it comes to selecting the most suitable analytical technique for trace and ultratrace analysis? This schematic shows some of the most basic but really crucial information needed to make this decision. So for example, what is your material made of? What form is it in? A liquid, a gas, a solid? What elements are you interested in? What are their expected and/or required concentration ranges? How large is your sample? Do you need an average bulk composition of the entire sample, or do you require small-scale spatial distribution information of impurities, such as depth profiling or surface analysis? And finally, a very important question is, are qualitative results sufficient enough to answer your questions? For the last point, it is important to emphasize that nearly all of the analytical techniques we'll be discussing today can provide both qualitative and quantitative information, and one can be no less informative than the other. This schematic illustrates the workflow typically taken for qualitative analysis. So every analytical technique starts by taking qualitative measurements, and qualitative forms of information can provide valuable compositional information as well, such as the amount of element present in a sample relative to another, such as the primary matrix, as well as imaging and distribution information. One excellent example is in high purity materials. If we know that a material is between 99 to 100% pure, a qualitative analysis will tell us specifically the ratio of any ultratrace impurities relative to the matrix or primary element. This allows for accurate and direct comparison between multiple samples and can often be much faster than a quantitative results. So it's only through analysis of reference standards with similar compositions to the sample, with accurately known concentrations of some or all of the elements of interest, and typically complex data reduction methods, can these qualitative data be converted into a quantitative concentration. Quantification requires the systematic testing and development of standard operating procedures, which is a time-consuming process, requiring round-robin testing at independent labs and/or publication of methods standards with bodies such as ASTM. For many advanced materials with unique or unusual compositions, there simply are no reference materials available. We can work with you to develop a reference material that would be used to quantify your samples if one is not available commercially, but unless you specifically require concentration information for regulatory or other reasons, it's important to bear in mind that many questions to material problems can be answered by qualitative data generated much faster and more affordably than quantitative data. Okay, so now let's move on to the specific techniques we'll be discussing today. This flowchart demonstrates all of the techniques we'll be focusing on. These techniques are extremely broad in the types of information they can provide, spanning from liquid or solution analysis and gas analysis to nanometer scale depth profiling. Here they have been separated into 3 key categories based on the type of sampling information they can provide. First, we have solution sampling, which can be done either on aqueous material or a solid sample can be taken and completely dissolved, allowing for its bulk analysis. Second, we have solid sampling, which unlike solution-based sampling, directly analyzes a solid material with minimal sample preparation. Solid sampling is generally defined by the size of the sampling area, which if large enough is considered to be bulk analysis. Microanalysis is typically defined as analysis of an extremely small amount of sample material or area, typically less than hundreds of microns or milligrams in mass. And then the third is spatial analysis, which is typically a solid sampling approach that can be done either in micro or bulk. So this table serves as a reference to compare the different analytical techniques we'll be talking about today. Based on the form of a sample, must be to analyze, the type of elements it's capable of analyzing, its detection limits, the sampling area, minimum mass required for a sample, and then their sampling capabilities. As you can see, no technique is perfect, and every technique has its limitations, but also has unique capabilities that make it compatible with other techniques. For example, IGA is the only gas-specific analytical technique and is capable of analyzing trace levels of hydrogen, carbon, nitrogen, oxygen, and sulfur in solid materials. SIMS, conversely, is a microsampling technique, solid microsampling technique, that has the best depth profiling resolution, but also has the smallest sampling area. GDMS can achieve depth resolutions and depth profiling of 10 nanometers or more, but has a much larger sampling area than SIMS. Conversely, LIBS, which is also a solid sampling technique with quite a small sampling footprint, but can be used to generate much larger sample maps up to 1600 millimeters squared in area. And finally, another example is ETV ICP-OES, which is really the only technique that can measure concentrations in extremely small amounts of sample down to PPT levels. As a more visual guide to the sampling capabilities of these techniques, here is a cross-section of a hypothetical sample with films and coatings showing the spot sizes and depth profiling ranges of GDMS, LIBS, laser ablation ICP-MS, and SIMS, as well as the techniques capable of investigating compositional variability on the surface and near surface of a sample. Also, shown to the right are techniques capable of characterizing the entire average bulk composition of a sample from surface downwards. And at the bottom, we have a simple guide showing which techniques are best suited for small quantities of sampled material, namely SIMS, laser ablation ICP-MS, LIBS, and ETV ICP-OES. To demonstrate the range of elements covered by all the techniques, which of course is very crucial information, here is a summary periodic table of all naturally occurring stable elements which have been color coordinated by technique and in some case their capabilities. So in this one, we can see the elemental coverage provided by GDMS in orange, ICP-MS, laser ablation ICP-MS, and GDMS in blue with an orange border, and then non-routine GDMS. So I just want to briefly mention that we haven't included LIBS and SIMS in these periodic tables because they provide complete periodic table coverage. GDMS, however, can cover all elements except noble gases with the carbon, nitrogen, oxygen, and can be done in special cases. ICP-MS and laser ablation ICP-MS can cover most elements apart from atmospherics, such as carbon, nitrogen, oxygen, and hydrogen, and the noble gases. And ETV ICP-OES, which we'll look at the next slide, can cover most elements apart from atmospherics and halogens, and instrumental gas analysis, again, can cover the atmospheric elements, including sulfur. So together, with all of these techniques, we have full periodic table coverage, and in the case where a technique is preferred, but does not provide all of the elements of interest, a combination of techniques can be used. So this table shows one of the most important features for purity testing, the purity grade N system, which represents the purity of a material defined by the number of nines from 100% total. The higher the purity, the higher the number of nines, and hence the higher the ends in the grade classification system. This is demonstrated in this third column here, which shows the total permitted amount of impurities within a material, expressed in parts per million, with ranges from 1,000 ppm to 10 ppb. We also have included the techniques we're discussing today and their sensitivities in relation to these purity grades. And we can see that our most sensitive techniques are SIMS, GDMS, ETV ICP-OES, and ICP-MS. So these techniques would be the best to consider when testing extremely pure materials or extremely small amounts. Okay, so now let's start looking at these techniques in a little bit more detail. First up is inductively coupled plasma mass spectrometry, or ICP-MS. ICP-MS and other solution-based techniques are considered amongst the most accurate and precise analytical tools, not only within Eurofins EAG's toolbox, but throughout the world of analytical chemistry. The strength of this technique is due to the fact that the samples analyzed are aqueous in form and analyzed by a very sensitive mass spectrometer. Solutions are introduced into a high temperature plasma, which ionizes its constituents before transport into a mass separator that allows for each stable isotope of an element to be detected. ICP-MS instruments also tend to be very sensitive with high dynamic ranges, meaning elements with concentrations ranging from very low to very high concentrations can be measured simultaneously. Sample solutions are typically analyzed alongside synthetically prepared reference standards for calibration. However, the most crucial process in ICP-MS is ensuring that solid material is completely dissolved or digested into a solution before analysis. This means that ICP-MS is strictly speaking a solution-based analytical technique, can also analyze the bulk composition of solid materials if they can be digested. And naturally, many liquid samples such as water can also be analyzed with minimal sample preparation. Now, sample preparation is very critical for ICP-MS analysis, but also potentially a risky step, as it can be a source of contamination or incomplete digestion. It is also not possible to even digest some materials, such as extremely hard sintered ceramics. But here we have an overview of the more common approaches to sample preparation for solution analysis, with pre-digestion for bulk analysis on the left, strategies for surface sampling in the middle, such as rinsing, and methods used to achieve complete dissolution or digestion of a sample on the right, typically achieved with solvents or acids, such as hydrochloric, nitric, and HF acids. So during these processes, care must be taken with particularly volatile elements or elements that have strong affinities to forming complexes with acids such as silicon and rare earths that can form fluorides when HF is used as part of the digestion procedure and can be therefore lost by volatilization. Therefore, each method must be rigorously tested for the efficacy, recovery, and reproducibility of the target elements, and must be carried out in a safe environment and using tools that minimize the risk of potential contamination. But saying that, ICP-MS, just a little bit more information about the technique as it is. It's very sensitive. It can sample quite small amounts of sample material. It provides high precision and high accuracy bulk quantitative analysis of trace elements in both solids and liquids. It's excellent for leaching studies, for example, regulatory compliance, and process and quality control testing. Suitable materials for ICP analysis include inorganic solids, such as ceramics, metals, alloys, oxides, semiconductor material, catalyst material, plastics, polymers, precious metals, and then organic solids, such as biomaterials, phosphates, carbonates, cosmetics, for example. And then, of course, liquids, such as water, reagents, and surfactants. ICP-MS's unique strengths is that it's universally accepted as a gold standard bulk chemical analysis technique with excellent sensitivity and high degrees of accuracy and precision. However, there are some limitations to the technique. Some limitations include the inability to provide spatial information in solids, difficulty in determining gas-forming elements, and dependency on achieving 100% dissolution during sample preparation. Another important concern is the presence of interferences due to polyatomics formed within the ICP-MS instrument between gases and sample matrix, gas interferences directly from the gases used during analysis, natural isotopic or isobaric interferences. Accounting for these interferences is a crucial part of the ICP-MS process, and various hardware and data correction solutions are used to minimize or eliminate their effect on results. However, it is these limitations that make techniques that do not require digestion, called solid sampling techniques, to be so valuable. However, if you'd like to learn more about ICP-MS, please see the link included, which will take you to a recent webinar that we held on the technique. So to summarize, solid sampling can sometimes be the preferred method for testing of trace and ultra-trace elements, as they involve minimal sources of contamination and minimum sample preparation. Importantly, they can be used for both bulk analysis, similar to ICP-MS, but also provide micro-scale spatial information on the distribution of trace elements in a material. So next, we'll be looking at some solid sampling techniques that excel at trace element analysis, both in bulk and using microsampling. These are glow discharge mass spectrometry, laser-induced breakdown spectroscopy, laser ablation ICP-MS, secondary ion mass spectrometry, and then we'll also be looking at instrumental gas analysis and electrothermal ICP-OES analysis. So first up, we're going to be looking at GDMS. GDMS, or glow discharge mass spectrometry, is one of EAG's most successful kind of areas. We have the largest number of GDMS instruments in the world. There are various configurations of these instruments, allowing for a range of different capabilities, including bulk sampling and depth profiling. It's a solid sampling technique that uses a beam of argon ions and atoms to strike the surface of a sample to remove atoms from it in a process known as sputtering. These atoms and ions, the atoms are removed layer by layer and become ionized, and are then transported into a magnetic sector mass analyzer, where they are separated by their mass charge ratio for measurement. GDMS has a relatively large sampling area, and that is hence why it can be considered a bulk technique. It does provide excellent resolution, depth profiling information. However, within that area, it provides full survey measurements apart from noble gases and hydrogen. It is excellent for analysis of difficult to digest materials. Provides depth-specific trace and ultra-trace distribution measurements down to ppb levels, and is excellent for traceability of unknowns from a limited amount of sample material. The types of materials that we can analyze by GDMS include advanced materials such as metals, alloys, graphite, electronic materials, oxides, glass, and ceramics. Films, thin layers and coatings such as environmental barrier coatings and semiconductors. Powders such as graphite, oxides, and metals. And GDMS has many unique strengths, making it very successful and very reliable instrument to use. It provides full quantitative elemental survey, high mass resolution, allowing for detection of ultra-trace elements. It can analyze conductive and non-conductive samples. It has very traceable test methods, extremely reproducible technique with, for example, an annual reproducibility of results and measurements of less than 10%. So it's excellent for long-term or multiple batch process control analysis. It can analyze multiple sample geometries and provide high-resolution depth profiling information. The main limitation really with GDMS is the assumptions that go into assuming the homogeneity of the sample. And although it could be considered a bulk technique due to the relatively large sampling size, we're still assuming that the area being sampled is going to be representative of the bulk composition. So just to demonstrate some of the materials that GDMS really excels at working with for purity surveying, here are some of the routine materials we certify, including semiconductor materials, sputter targets, medical stents, for example, high performance ceramics, fuel cell material. But if you would like to learn more about GDMS, we had a webinar recently. Please, as part of the Smart Chart series, please see the link included, which will take you to where you can register for that. So next up, we move to our first microsampling technique, laser-induced breakdown spectroscopy, or LIBS. So LIBS uses a nanopulsed laser beam to hit the surface of a sample and remove material from the surface, causing it to be atomized and ionized in a process called laser ablation. The ablated material is then directly measured by an optical emission spectrometer located directly above the sample, allowing for near instantaneous and direct measurement of the elements ablated by the laser. By moving the sample around in an automated cell with a calibrated motor, this approach allows for spatially resolved mapping of element distributions over a much larger area than the initial laser spot. LIBS is very versatile in its sampling capabilities. It can analyze any element and most materials. It is also extremely rapid, capable of measuring, for example, a 40 by 40 millimeter area map in approximately 10 minutes or so. It can provide depth profiling, 3D mapping of trace elements down to 1 ppm, and it is reproducible over long term. Suitable materials, there's not many limitations on what materials we could look at. It could do most inorganic materials, granular materials, and organic materials. So combined with its spatial mapping capabilities of any trace element, another significant strength of LIBS is that we can analyze atmosphere-sensitive materials using a custom design sample cell. Large maps also generate thousands of spatially resolved data points, allowing for detailed statistical analysis. However, there is a big caveat with LIBS, and that is the need for matrix-matched reference standards for quantification purposes, which can be very difficult to obtain for some materials and elements, particularly those of more complex structures, such as coatings, or elements that are very difficult to quantify by other bulk techniques. But if you would like to learn more about LIBS, please join us in 2 weeks for our upcoming webinar as part of the Smart Chart webinar series. So our next up is another solid sampling technique called laser ablation, ICP-MS, or inductively coupled plasma mass spectrometry. Similar to LIBS, laser ablation, ICP-MS, uses a laser beam to remove material from the surface of a sample. Instead of being analyzed at the site of ablation, however, the ablated material is transported in helium and argon to an ICP-MS, where it is ionized and analyzed for its elemental constituents, just like solution-based ICP-MS, but without the digestion preparation step. And instead of synthetic standard solutions, laser ablation ICP-MS requires the analysis of matrix-matched solid reference standards alongside samples for quantification. And in fact, EAG has thousands of solid reference materials for this very purpose. So laser ablation ICP-MS has one of the smallest sampling foot sizes. We can do a sampling spot of approximately 10 to 20 microns in area. It has ppm or high-level ppb detection limits. Its main limitation is that it cannot analyze noble gases or atmospherics. And it can do some depth profiling, but we do offer better techniques for that purpose. So its ideal uses are for chemical analysis of solids for full survey. It really is excellent for near surface local inclusion and defect analysis, or samples that are difficult to digest for ICP-MS analysis. It's excellent for ROHS testing, and the suitable materials that we can do laser ablation ICP-MS on, and we have reference materials for, include materials such as glasses, optical displays, manufactured minerals, abrasives, alumina, sapphire, ceramics, matrix composites, mining products, cement, sediments, rocks, for example, and then metals, alloys, and solders as well. So The unique strengths of laser ablation ICP-MS is that it provides surface and near surface analysis, analysis without pre-preparation at all, and the direct elemental analysis of most solid materials. Its limitations are that it does require matrix match standards for quantification. We're limited by sample structure and sample homogeneity. We're also limited by similar problems with interferences like solution-based ICP-MS, but we do take many steps in our data reduction process to avoid those. And then also there's a few other instrumental and sample-based kind of limitations that can occur. But we'll be going over these in much more detail in an upcoming webinar as part of the Smart Chart series, specifically on laser ablation ICP-MS. So please join us for that. Our next technique is, again, another versatile technique. It's a solid sampling technique called secondary ion mass spectrometry, or SIMS. It's considered a microsampling technique, but provides depth profiling, 3D mapping, and near surface. EAG is very proud that we are the industry standard for SIMS analysis, and we have the largest range of SIMS instruments worldwide, more than 40. SIMS, the principles of SIMS, basically is the sample surface is sputtered or etched with a beam of primary ions of doubly charged oxygen or cesium, the latter of which is used to analyze atmospheric elements such as hydrogen, carbon, oxygen, and nitrogen, which expands the elemental capabilities of the technique. Secondary ions formed during the sputtering process are extracted and analyzed using a mass spectrometer, of which there are multiple configurations, providing a range of capabilities such as depth profiling. Quantification does as well, similar to other microsampling techniques, rely on analysis of ion-implanted and bulk-doped solid standards. And actually, EAG has, to our knowledge, the largest SIMS reference material library in the world. SIMS has excellent detection limits, a very small sampling area, and excellent depth resolution capabilities. These are really what it excels at doing. It does provide bulk analysis though as well. And it is excellent for composition and purity measurement of thin films and bulk analyses of elements such as carbon and oxygen, nitrogen, and silicon. So suitable materials for SIMS analysis include thin films, ion implants, shallow implants, and ultra thin films, and bulk semiconductor material. Its unique strengths are that it's excellent for samples with very limited volume or very small area of interest. It has the highest accuracy analyses of dopants or major impurities in semiconductor materials. Excellent detection sensitivity, excellent depth resolution, detection of all elements and isotopes, so full periodic coverage, including hydrogen. It has a wide dynamic range, and it is possible as well in some cases to provide stoichiometry information. Its limitations are that it requires standards for accurate quantification. It assumes information about the homogeneity of the sample, which can either be ascertained by assumption or by sampling multiple areas of the sample. And it requires a specific list of elements for analysis because conditions for analysis need to be optimized specifically for those elements to achieve the best detection limits. But if you would like to learn more about SIMS and our SIMS capabilities, I would like to direct you towards our website, which has a wealth of SIMS resources, including tutorials and application notes. And I believe we'll be providing some links to some webinars as well. So next up is the first of our two kind of unique techniques, this instrumental gas analysis, or IGA, which is a solid sampling technique. It's considered a bulk solid sampling technique. Instrumental gas analysis analyzes gas-forming elements that reside in a solid material, either through chemical bonding or that are trapped in the lattice structure as gases. These elements are hydrogen, oxygen, carbon, nitrogen, and sulfur. So basically, a high-temperature furnace is used to rapidly heat the samples and thereby convert certain elements into volatile forms in order to separate, detect, and measure them. And IGA is really an industry standard technique for analyzing gas-forming elements in materials like steel, metals, and alloys. It has excellent detection limits, ppm levels, and although it doesn't provide any spatial information, it is really kind of the go-to for looking at your quantitative gas information. It's suitable for solids, powders, or particulate materials. In some cases, it can provide fractional gas information as well, such as to inform about bonding chemistry. It can provide surface versus bulk information. And it is used as a highly complementary part of a kind of a suite of analyses that are used in conjunction with SIMS, GDMS, and ICP-MS. Materials that IGA is suitable for include metals, alloys, semiconductor materials, ceramics, graphites, carbides, and then oxides, carbonates, for example, materials like that. So the unique strengths of instrumental gas analysis is that it is very well established. So there are multiple standard methods and operating procedures available. It's rapid, a high throughput, so it can analyze many samples and rapidly. And it can also provide hydrogen and oxygen environment information, both on surface and bulk, using a combination of different temperature programs and reaction agents. And it is precise and accurate as well. However, the main limitation in that it's a bulk technique is that it requires a relatively large amount of sample, typically between 0.5 gram or more per subsample. And it does require complete destruction of the sample. But if you would like to learn more about instrumental gas analysis, please see the link included, which we'll be providing you, which will take you to a recent webinar as part of our Smart Chart series on specifically on IGA. And for our last technique, we're going to be looking at ETV ICP-OES. That is electrothermal vaporization, inductively coupled plasma optical emission mass spectroscopy. A little bit of a mouthful, but this is a very powerful technique for rapid, direct determination of trace analytes and ultra-trace analytes in a broad range of samples, including solutions, slurries, and solids. It requires minimal or no sample preparation. Effectively, this solid sampling technique uses electrothermal vaporization of a small quantity of sample, which is then transported to a high temperature plasma similar to ICP-MS, where it is ionized and its elemental constituents measured by their emitted light using a sensitive optical emission spectrometer. This technique offers exceptionally high sensitivity and enables rapid chemical analysis. Sensitivity is considerably higher than traditional ICP and ICP-OES, however, due to excellent analyte transport efficiencies. This means we can analyze very small amounts and achieve very high, excellent detection limits down to PPT levels. The main limitations for elements is that ETV cannot analyze gas and halogens, but other than that, it has excellent coverage. So its ideal uses are to provide direct determination of ultra trace level contaminants in solids, liquids, and slurries. It's capable of analyzing small sample sizes. So if you're producing a material, for example, that is very expensive to manufacture in bulk, but you need to know the impurity levels, ETV could be an option for you. It does provide up to 15 elements at a time it can analyze. And again, it's extremely sensitive. It is proven to work very, very well with ceramics, silicon carbide, graphite, and refractory oxides. So those materials that are traditionally difficult to digest or analyze by typical ICP-OES or MS techniques. And the unique strengths of ETV ICP-OES. It's extremely sensitive. You can add different chemical reaction gases and modifiers for unique solutions to particular materials. It's fully automated. It allows for direct determination of elements in organometallics. Its limitations, however, are that it requires accurate and precise weighing of samples. The analyte released from a sample can vary based on the sample matrix and form. It assumes representative sampling. And really important, though, is the release of a particular analyte can vary based on the specific sample matrix or form. So each material element must be tested for precision and proof of method. Okay, so in summary, this table provides a succinct overview of the main capabilities of our trace and ultratrace analytical tools here at EAG, each with their own unique capabilities that provide a wide range of services, and when used in combination, can provide bulk and spatial information of any naturally occurring element in the periodic table, and which of these you should consider when choosing the best technique for your material and material problems. So for example, SIMS, GDMS, ICP-MS, and ETV ICP-OES are ideal for ultratrace analysis. And SIMS can provide quantitative noble gas analysis, whereas LIBS can provide rapid testing for their presence and distribution over a large area, here and here. SIMS, GDMS, and LIBS can provide spatial depth profiling information, but each have different sampling sizes and depth resolutions. It is also important to remember that a combination of these techniques may be needed to solve particular problems. But if you would like to find out more about the specific technical capabilities of each of these techniques, or learn about some case studies and applications that combine these techniques, please check out our past and upcoming webinars, application notes, and white papers, all of which are available on our website, or go ahead and reach out to us directly. We'll be very happy to answer any questions you have. So just briefly, why choose EAG for your analytical trace and ultratrace analysis? There are several reasons, but I think it's important to state right at the top that client confidentiality is core to our business. We are a global leader for material testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering-related issues. Finally, in the light of the pandemic that is affecting all of us right now, I want to stress that EAG Laboratories is committed to the safety of our staff and clients. Worldwide, we have complied with the latest COVID-19 regulations from state and local governments, as well as the CDC. Currently, all of our locations throughout the world remain open, but we may have some limitations on customer visits, as this is a fluid situation where we are operating a laboratory at reduced capacity. We can also transfer your samples to another EAG location should that be needed. We encourage you to discuss your options with our sales representatives.